So in chapter 2.2, we're going to look at limits that do not exist and a couple of things to keep in mind. As we mentioned before, that we can approach a certain point, and in this case, we are approaching zero, the time zero, and we can approach that in a table as we have done before, so that our time, as we enter our time, can be 0, 0.1, 0.01, and we get closer and closer to 0. Well, this table that I've just created would be from the right side, because it is just a little bit larger than 0. So therefore, I would notate this as a limit of t for time. That's our input value. So that's where we put it, is down here. And it's approaching 0. And to designate that it's from the right side only, we're going to put a plus sign at the top right of our value there. Then we would write the function. And in this case, our function is h of t, which stands for the engineer that created this particular function, an electrical engineer, Heaviside. So we just write that function as h of t will equal some limit. I haven't calculated h of t. Therefore, our general notation for approaching 0 from the right side looks like that. So as we approach 0 from the left side, we would want something smaller than 0. In that case, it could be negative, and we'd have a negative, and it would be simply the same. We could use the same 0.1. We could say negative 0.01 and negative 0.001. And we would notate that, again, we would notate it as the limit of, and this is how I typically state it, I think this is how the book states it as well, is it as the limit of, and state the function, h of t, for t approaching the value 0. We put a negative sign at the top right of the 0 to let us know that we are approaching 0 from the left. And again, we would state that as it's approaching 0, that is going to give us a limit. The reason that we have left and right side designations of limits is so that we can find out when we calculate our set tables, is the value of the left and the right side approaching the same value. So let's take a look at this graph or illustration. And notice that as we approach 0 from the left, our output value is going to be 0. So on the left, as we approach 0, our set value is 0, 0. So from the left, as the limit of t is approaching 0 for the function, we are approaching the limit 0. From the right side, however, as we are approaching 0 from the right, our output value is 1. So we would say that our limit for the function h of t as t approaches 0 from the right is 1. Because 0 is not equal to 1, we would say the limit does not exist. For a limit to exist, you must be approaching the same value from both the left and the right side. So let's take a look at another illustration that the book has. And as you can see, they have the notation here on the left-hand side. And this is in general notation, meaning that there are no actual values, but they're all variables. And we can say that as we are approaching a from the left, and that's what it shows here, that we're approaching some value a, and a is this point right here. And we are approaching a from the left. So as we are approaching it, we're going to call x, and we will just say that x is a point to the left of a, and we would say that this is a one-sided limit for x approaching a. And of course, they have the general notation set up for you so you can see that. And they've done the same thing here in the illustration on the right. It is approaching a if we call that point on the graph x. We can see that that point, that x is approaching a from the right side. And here we can see that general notation. So let's take a look at just a couple of graphs. Let me see here. So I'll just make up a couple of graphs or curves. And remember, a curve can be a straight line. We call any function that we are graphing a curve. So even if I had a straight line, well, that's not straight, but if I had a straight line, we would still call it a curve. So if I have a curve like this, we call this is called continuity. Continuity refers to a graph where you can begin and end from one point of the curve to another without ever picking your pen up off the paper. So this graph that I'm showing you has continuity. Because of that, we know that regardless of a point that we create on that curve, and we'll call this A, we can approach it from the left and from the right, and we will always be approaching the same value. Whenever a graph has continuity, we know for sure that it has a limit. So this will always have a limit. Some functions that you're going to see which have continuity are going to be the polynomials that we've worked with in basic algebra on up. So if I gave you a function, f of x is equal to x squared plus 3x minus 13. This is a polynomial. We know that solutions for every input of x, we will have an output for x. So it has continuity, meaning the graph will never have jumps or holes. So let's look at a jump. If this cooperates. Similar to the graph that we saw up above, if we have a graph that jumps, and starts again, we know that as we approach point A from the left, that it's going to have a different value. We're going to approach a different value than if we approached A from the right. We would say that the limit for this graph does not exist. Later on, we will learn mathematically how to determine if a limit exists or not, purely from the function. You can already imagine that setting up a table will also give you an idea if the limit exists by setting up a table for values less than A and values greater than A, and seeing if, as we approach the value A from the left and right, if those values are getting closer to the same value. If not, it does not have continuity. It may have a jump, such as this graph, or a break, whereby the values are not the same and the limit would not exist. So I hope that helps. And again, thanks for watching.